This is pure pine wood that I chopped up a couple of days ago. What I will do with this material is to investigate what happens when we heat it. So I will take some of those chopped up pieces. I will put them in this glass cylinder. Wood doesn't burn, liquids don't burn, but the gases burn. What's wood made of? Cellulose. Cellulose is one of the main components. Actually, two types of cellulose. About 50% is cellulose, 25% is hemicellulose, I don't know the difference, and the rest of the 25% is lignin. Yeah, and what's lignin? Lignin is like nature's own glue. Cellulose, that's like, let's say, loose paper fragments. To have a structure like this, you need to glue it together. That's what the lignin does. It holds the cellulose together. So lignin is like nature's own glue. So basically, this is cellulose, lignin, and there's one more important component. Water. This has been stored inside for, let's say, 2 or 3 years, under roof, inside, room temperature. But I can guarantee there's at least 10%, weight percent, of water still in this material, still in the wood. The only way to get it completely water-free, what would that be? If I want this completely water-free, what do I have to do? I have to store it in temperatures above 100 degrees. Then the water will disappear. It will evaporate. But if I keep it under 100 degrees and in normal room temperature, it will adapt the moisture from the air, and it will actually stick to the cellulose fibers. So at least 10, probably 15% of water. So in order to put this on fire, what do I have to do? I need to break the structure because cellulose doesn't burn, lignin doesn't burn, but if I break down, cellulose is a very, very long, in the molecule world, a very long chain molecule. It's solid, it stays there, and nothing that stays there can burn. We need to get that one in gaseous phase. So what I have to do is that I have to add energy or heat. If I add heat to a long molecule, what will happen? You will break it. It will break up in smaller parts. And in the molecule world, it works like this. If you have very big molecule, the likelihood to find them in solid phase is very, very big. If you have very small molecules, it's probably a gas. So the smaller the molecules, the more likely it's a gas. If I add heat, this long chain molecule will start to break apart, become smaller molecules. Hopefully, a gas. And if it's a gas, it will leave the material. And we're going to see what kind of gases that will leave the material if we start heating it. So now we're adding a lot of heat. As you can see, I'm using the pre-mixed flame. I want high temperatures, 11, 12, 1300 degrees. The glass will adopt the same temperature. Now we can see white smoke in the canister. What's that? Water vapor. The steam is leaving. The water is evaporated at 100 degrees. That's the first thing that will leave the system. And you can see it creates an overpressure. And here it comes. Most of this is water. And for obvious reasons, water doesn't burn. It's not flammable. Does not burn. It actually almost extinguished the flame. It has a hard time here. So a lot of water. You can see a yellow color. What's the yellow color? The breakdown of the wood has started. Some of the pyrolysis products have different colors. There's also tar. You know tar in the wood? That probably becomes kind of yellow. Now the cellulose is breaking down very heavily. It's forming a lot of different gases. Depending on what temperature, like the book says, under different temperature intervals, different products will be formed. Right now it's not extremely hot in there, but can you see the liquid? There are droplets coming out, liquid ending up on the ground. What's the liquid? Condensed water, and tar is also being condensed. So we're moving into breaking down the cellulose very heavily. More and more of those combustion products are being formed, or not combustion products, but pyrolysis products. I'll get rid of some of the condensed water again. And water is being condensed because when it hits the rubber, that's not more than 100 degrees. It goes back to. So there's still a lot of water. Not very good, not extremely flammable, but now and then there are some products in this that's obviously flammable. Getting better and better. You see the quality is getting better, burning, cleaner burning, more sustainable burning. Now we're getting really good products out of this. Okay, there's an overpressure because the bag grows and grows and grows. If I hold it long enough, it will explode, or this one will go. Take it out. Not very hot, almost like room temperature right now. Definitely flammable. Even in room temperature. Don't need to be heated. Still some water. Most of the water is probably gone, but there's still some water coming out. But the water is being mixed with more and more tar. You can see the color of those droplets. Dark brown, yellow, a lot of tar. And of course, the quality of this is getting even better, better and better. A very nice flammable gas is being formed in there right now. I'm going to take this process for a couple of more minutes so that all the wood is broken down. Takes a couple of more minutes. So if I ignite it here, isn't there a risk that it goes back and we have an explosion in the glass bulb? It's completely free of oxygen. No oxygen whatsoever inside. So no problems with igniting that one. It won't go back. As you can see, the process is slowing down. There's not much leaving. It's slowing down. That means that almost all the wood is being transformed or broken down. There's not much actually leaving more. So we'll let it cool down for a couple of seconds. What's left? What's inside? The same amount, almost the same size. Not a very big difference. The only thing that has changed is the color. Or twice or 3 times as heavy. So something has left. Something has disappeared. So what has disappeared?
Water.
Water has disappeared. That makes like 10 or 20% of the weight, definitely. Water is gone. What more is gone?
Some molecules from the cellulose.
Yes, molecules from the cellulose has left. An even easier question, what's left? What's this? Coal. It's pure coal. It's the, what do you call it, in the periodic system, it's coal. C, pure C, nothing else. Only coal left. We tried to pyrolyze everything that was inside, but the coal didn't pyrolyze or decompose. Why didn't the coal decompose? There was no oxygen. 100% oxygen free. And coal being in the periodic system, substances in the periodic system, you cannot break them down. They're as far as they can go. Coal cannot be broken down. It's impossible to break down coal. You can oxidize it if there is oxygen, but you can't break it down. Cellulose you can break down into smaller components. Coal can never be broken down. Coal is coal. So, can this burn? Yes? So let's try. It's coal. Yeah, we saw that yesterday. Let's see if we can make... we saw that the things leaving this could burn. So does it burn?
Yes.
It obviously burns, but with a big difference. What's the difference? There's no flame. And that one burns with a flame. But the only reason that this burns with a flame is that those components that we just cooked away, they're still here. The gaseous components. But in this, they are already gone. So here, they're still there. It will burn with a flame, gaseous component leaving the material. But here, they're already gone. So, same procedure as with the metal. This is a surface oxidation. This is a decomposition of wood and a flaming phenomena. Surface oxidation. So, next little question. If we let this process go on, what's left? What's left in the barbecue in the morning? Ash. Some gray dust. So, what's ash? We've taken away all the gaseous components. We've oxidized the carbon, but there is still something left. This gray stuff. What's that? This. You see? What's that? Still there. Impossible to oxidize. Impossible to burn. It's still there. No matter what circumstances I put it under, it doesn't burn. That wasn't entirely true, because during the time, the period that the tree was still alive, it was sucking up water and nutrients from the ground. With that water and with those nutrients, there will be certain things that are already oxidized, like stone, for example, minerals, some kind of metals, metal oxides that are still already oxidized. Those will be in the wood. They will not disappear when I do the decomposition process. They will not be oxidized again because they're already oxidized. They will be the ash. So minerals, whatever, are still there. So that's actually the gray stuff. Perfect to put on your flowers because pure nutrition. It was what the wood was using, the tree was using for its own nutrition purposes. Put it back in your garden and it's perfect. So what's left when we've taken away everything that's possible to get into the gaseous phase is pure carbon. Nothing else.